Hi, and welcome to Science for Schools. In this episode, we're going to be investigating how light is reflected by a mirror. So we have our light source over here. There's a mirror, and just to help with measuring exactly how it's affected, I've got this piece of paper where I'm going to put the mirror on this line, and this line here is exactly perpendicular to that, and I'm going to try and get the beam to hit exactly there. So first of all, let's just get the beam to hit the mirror at this angle. And try and line up the mirror so that the actual reflecting part is on the line, not the glass in front of the mirror. So there it is. I'm just going to mark the path of this light so I can do some measurements a bit later. Just about there, and coming out about there. And that's all I need for the moment, because I can finish those lines since I know exactly where it's hitting the mirror. And I'm going to try and get another angle as well. Just get a narrow one. And again, try and get it to hit that spot as much as possible. And line up the back of the mirror, the metal part, the reflecting part of the mirror, with that black line. I'm going to mark the path of the light. Okay, so I'm going to finish these lines, connect them both to where the light hit the mirror. And likewise for the other line. Once again, try to aim it at the same spot in each case. So you can see we've got certain angles on our side. The light coming in on this red line here comes in at an angle. We usually measure it from this perpendicular line that we call the normal, and hopefully you should be able to see, and you can measure this with a protractor, that the angle on either side of this normal is the same. And likewise for the green line, if we measure the angle from the center to each of those light beams, if you measure those angles, hopefully they should turn out to be the same as well. So thanks for watching, and I'll talk to you in the next episode.
Okay, so now we're going to look at the convex lens. A lens is a device that makes images by refraction. A mirror is a device that makes images by reflection. So we're going to look at how to draw ray diagrams for a convex lens. The convex lens bulges outward slightly at the center. So we're going to look first at a surface that bulges outward. Let's go back. Bulges outward, and you see the light that enters the lens has to bend toward the normal because the lens will have a larger index of refraction than air. And because the lens is curved, the normals are not parallel. The normals point in different directions. But rays that enter into the lens always have to bend toward the normal. And for the same reason, rays that come from the lens and come out have to bend away from the normal as they leave. So here's a convex lens, and I'm using a thin lens approximation instead of a thin mirror approximation. So the ray doesn't actually bend in the center of the lens, and we need to be careful to understand that. The ray bends downward when it comes into the lens, since it bends toward the normal, and then because the other side is curved in the opposite direction, the ray also bends downward when it comes out of the lens because it has to bend away from the normal. And therefore two rays that come in parallel will form a real focus on the far side of the lens, a real focus. So those are going to be our two principal rays. A ray that comes in parallel to the normal will refract through the focus, and a ray that comes through the focus will refract parallel to the axis. So here's how we draw this in the case where the object distance is greater than the focal length, here's my image. It's outside of the focus on one side of the lens. My first principal ray is parallel to the axis, and it has to come out through the focus. My second principal ray passes through the focus and hits the lens, and that has to come out parallel to the axis. So these are our two rays, and our third ray, our third principal ray, will travel directly through the center of the lens. I didn't draw this perfectly. Will travel through the center of the lens, and will travel straight through. So that's our third ray, and you see we form a real inverted image on the back side of the lens. The image is real. This is really the crucial part. The image is real because the rays pass through the lens, and then the rays themselves converge to form an image. That is the defining attribute of a real image. That's formed by the rays and not by our own imagined extensions of the rays. We can work out the equation that relates distances and sizes, and this is exactly the same derivation as for the concave mirror, and so you've seen this before. Here are our blue triangles, and you can go prove them similar. We have HO, we have HI over here, we have the distance focal length F, and here's the distance DO minus F. And you can write exactly the same equations as we did in the case of the concave mirror. And you should do this. Take the time to do this. Do the blue triangles, do the red triangles. And with the two equations for HI over HO, you should be able to derive this equation. Follow what we did in the other video, or you can follow the derivation from the notes, but make sure you understand it. And then finally, from our third principal ray, we have green triangles. Again, this follows exactly the discussion that I gave you in more detail for mirrors. So if the image is now inside the focal point, we can still draw the first principal ray easily enough. For the second principal ray, though, we cannot draw a ray through this focus because obviously we're going away from the lens. I hope that obviously. And if I aim a ray going this way, it has to refract downward. So that's not going to work. We can't draw through here. So what we do, and we use this trick for mirrors also, is with a ruler we identify this line. See? We identify this line. And this line will define a ray that, as far as the lens is concerned, it came through the focal point, because this is the direction of a ray that came through the focal point. So it has to come out parallel. All the refraction occurs up here at the top of the lens, and it doesn't really matter where the ray originated as long as it's coming on this line. And you see our two principal rays diverge on the far side of the lens, and therefore no real image can be formed out here. However, these rays can be extended backward. And again, from the equation of the lenses, I'll just note this one more time, one can prove that the image is formed back here, and that all the rays that are emitted from this object, reflected from this object, will all appear to be emitted from this point, and therefore we get a virtual image. It's right side up, and it's larger than the object. This is the use of a convex lens as a magnifying glass, and you can go outside with the lenses that we have. And you can practice, you can burn some paper by having sun's rays focus at a point. You'll have a wonderful time doing all this, I'm sure. So that's it for convex lenses. Have a good time.